Okay, more matroid polytopes.
Do you want this to do anything, or okay? Like, yeah. Should I click on the record now, or all the one?
No. It should be okay. So my goal for the last few lectures and for the next 2 lectures is to keep convincing you that matroid polytopes are amazing objects, and they have very nice properties. So far we've seen several things. For example, we've talked about the vertex description and how that corresponds to basis of the matroid. Last time I proved a theorem describing the edges of the matroid polytope. So we said that every edge is a vector of the form EI minus EJ, and you can think of each edge as encoding a basis exchange. In other words, all the edges look like this. You have a basis, B, and then a basis where you remove something and you add something. And this is what the edges look like. And they are of the form EI minus EJ. Okay? Now, one thing that I want to point out to you is that I also gave an inequality description. So I gave you the vertex description, and I proved the inequality description that said, well, I had an inequality description that said something like this. The inequalities looked like this. Then we had inequalities like this and an equality. But one thing that I didn't say explicitly is that this is not necessarily what you would regard as the facet description, because here I gave you a bunch of inequalities, but it would be more precise if I just told you exactly which inequalities you need and which ones you don't need. In other words, which inequalities define facets and which ones do not define facets. So that's something we don't know yet. And there's something even more basic that we don't know that we've been wondering since the first day that we saw these matroid polytopes. And this is a question that Jameson asked me, which is what is the dimension? We don't even know. We saw that matroid polytopes seem to have different dimensions, and I haven't really given you yet the description of the dimension. Okay.
Can I ask a question?
Yeah.
How unique are these things? I mean, like the 2 matroids, like these things don't see loops for one thing, right?
So your question is basically to what extent can I reconstruct the matroid from the polytope?
Yeah. Is it just that it misses loops, and other than that, you can figure it out, or is there more?
So that's a good question. So maybe I should put it here. Question, given a polytope, what can I say about, to what extent can I recover M? For example, 2 things that are not too difficult to see is that the polytope doesn't notice loops or coloops. I mean, okay, the polytope doesn't notice whether M has loops and coloops. Now, of course, if I give you the coordinates of the polytope, then you can just, from the coordinates you can just read off the basis directly. But the question is, what if I just give you the polytope? I give you this polytope. And we saw last time that this is a matroid polytope. And I ask you, can you tell me what the matroid is? Well, that think about that. Think about that, and this is not something we're quite ready to answer yet. But
It doesn't notice loops and co-loops because loops will, if there's a loop, then it will always have a 1 in that position in the basis, or a 0 in that position. And if you have a co-loop, it will always have a 1, so it'll just change the dimension of the ambient space.
right, so for example, we saw that this was the matroid polytope of our favorite graph. Okay. And this graph, in principle, the matroid polytope lived in R6 because this guy has 6 elements. But then we saw that actually the matroid polytopes just, every basis had a 1 for this coordinate because every basis contains the co-loop, and every basis had a 0 for this coordinate because no basis contains the loop. And so therefore, this guy and this guy are congruent polytopes. So maybe this one naturally lives in R4, this one in R6, but they both look like this. Okay, so the first thing I want to do today is talk about this dimension. Naturally, I mean, if I give you this description and you just look at it and don't think about it very carefully, then what dimension do you think this polytope is going to have?
Rank.
Well, first of all, where does this polytope live? In what dimension? R to the E, right? And so in principle, it should be a polytope of dimension the size of E. Now, it's not. And we know that immediately because there's an equality here. And this equality defines a hyperplane. And that tells us that our polytope lives on a hyperplane in RE. And it lives on a hyperplane, so therefore, because it lives on the hyperplane x1 plus xe equals the rank of the matroid. So you might think that the dimension is basically the dimension of the space minus 1. If you look at this superficially, then that's what you're going to think, because you live in RE and you have 1 equality. Okay? But there we have an example of a matroid polytope which lives in R6, yet it's 3-dimensional. And so the question is, what can make the dimension smaller? And this is what I want to talk about today. So for that, we have to remind ourselves of some theory that we talked about earlier. We have to talk about the direct sum of two matroids. So if you have a matroid on some ground set and some circuits, and if you have another matroid on a disjoint subset ground set, and a set of circuits, then we defined the direct sum. And we said that the direct sum was basically what we would get if we would kind of glue these matrices together and not have them interact in any way. By which I mean that you don't have any mixed circuits. The circuits of this matroid are either the circuits in here or the circuits in here, and there's no others. So that's what it looks like. Okay? It's just kind of gluing M1 and M2 without any relations between them. Okay? And so what you can do is if I give you a bunch of matroids, then you can you can take direct sums and build a bigger matroid. Okay, and this is the same situation as with multiplication with maybe natural numbers. If I give you some numbers, you can multiply them, and then the next question that you're going to ask yourself is, okay, well, if I have a number, then how can I express it as a multiplication of basic things? And that's the next question I want to ask is basically, what are the primes here? I mean, I can take direct sums, and now the question is, if I give you a big matroid, how can you write it as a direct sum of minimal things? So question, how can I write matroid M as a direct sum of minimal matroids? And what I mean by minimal is a matroid that you cannot break up into pieces, into a direct sum. In the composables. And so n is indecomposable if you cannot write n as a direct sum of matroids. Okay. So we're going to call a matroid indecomposable if you cannot break it up into two different pieces. Another question is, if I give you a matroid, how can you break it up into its indecomposable pieces? Okay. I'm going to show you how to do that. So before I make this definition, maybe I should let's do an example. So our favorite example. Okay. Here's a matroid. Now, can you take this matroid and decompose it into pieces? In other words, is this matroid a direct sum of smaller matroids? How can you do it? For example, you could do this. Right. So, right. So first let me say why this is true. That you see the circuits of this matroid are either contained in this part or in this part. But there's no circuits containing edges here and edges here. And that's why I can break it up. And for the same reason, I can also break up this call loop. Okay. Because again, there's no circuits in my graph that involve edges here, edges here, edges here. Now, it's pretty clear that I cannot break these two guys up anymore. What about this one? Well, if you think about it, you're not going to be able to break it up. Okay. And so what I want to do is say, for example, why can I not break up this edge and this edge? Because they're in a circuit together. Okay? So I can't break up into two pieces because that would break my circuit. And that's basically going to be the key notion here. I'm going to say that I'm going to define a relation. I is related to J if they are together in a circuit. There is a circuit containing I and J. And the point is that if you want to break up your matroid into a piece plus a piece, then you cannot have I here and J here. The reason being that there is a circuit here involving I and J. which will become a mixed circuit here. So this would not be a direct sum. And so this is basically going to be the obstruction. You cannot separate pairs that are related in this way. Okay. So, right, so the idea is if m equals m1 plus m2, I cannot have I in m1 and j in m2. That's my idea for defining this relation. Now, you should maybe be a little bit worried seeing me use this sign. This sign is usually read equivalent to, okay? And I should only use this sign if this is actually an equivalence relation. Now, is it an equivalence relation? Well, there's another. Before anything, the most primitive, simplest thing that an equivalence relation has to satisfy is that anything is equivalent to itself. Okay, so that's not too interesting, but we better define I to be equivalent to itself. So now I is equivalent to itself, and it's clear that if I is equivalent to j, then j is equivalent to I. And so the next question is this transitive? So if I is in a circuit with j and j is in a circuit with k, does that imply that I is in a circuit with k? Well, okay, I wrote proposition, so it's true. But this requires some proof, right? What does this mean? It means that I and j are in a circuit. This means that j and k are in a circuit. What can you conclude from here? Well, you have two circuits, and you have that they have an element in common. And so we have this circuit exchange that says I can conclude that there is some circuit E which is contained in C union D minus J. Am I done? I'm actually not done because, okay, so I found a circuit, but is this circuit the one I need? Well, I would need to prove that I and K are in the circuit. And so, I mean, this here I used some circuit exchange, but the point is that I'm gonna have to develop a stronger circuit exchange axiom that lets me guarantee that. So there's a circuit such that actually I and K are in it. And so this is a strong form of the exchange axiom. And I should say that this is not easy at all. This is one of these statements that seem pretty tame, but then if you want to prove them, well, we already got a lot of practice proving statements like this. We saw sometimes they're easy, sometimes they're just not easy. This is not easy, but it's true that you can get. Well, basically, it is true that you can prove this, but it's not easy. And so for details, you can see Oxley to see how he pulls this off. Okay. But so the point is that this is an equivalence relation. Yep.
So what exactly is the stronger exchange axiom? Like you usually say, is that right there?
So no, but actually, I was debating whether to bring up this technicality or not because it's a very subtle thing. Actually, this is false. This is false, and what is true, this might be false for C and D, but it might be true for a different choice of a circuit containing I and J, and a different choice of a circuit containing J and K. So it's even more subtle than I wrote it.
So it's like given I and J.
So what is true is this, basically. Okay? But this strong exchange action might not be true for this particular choice of C and this particular choice of D. You might have to use a different circuit here and a different circuit here. So actually, to give you an idea, it is kind of a strong exchange action, but this is not an implication.
So the strong exchange axiom is actually that proposition right there.
Basically.
That we can find if we have those two circuits, or a circuit containing I and J and a circuit containing J and K, we can find a circuit with I and K.
Yeah, basically, this is an easy, memorable circuit exchange axiom that is true. If I and J are together in a circuit, and J and K are together in a circuit, then I and K are together in a circuit.
Can you draw a picture of that, of I and J being in the same circuit, and J and K being in the same circuit? I mean, they're indifferent. They're I, J, and K are not in the same.
Can I draw a picture?
You have it.
Yeah.
I have it here.
Make I and J.
I and
Make I the, well, label the edges.
okay.
Okay, so if I was 3, and J was 2, and K was 1, right? So you have 3, 2, 4 as a circuit, and you have
3, 2,
1,
4
2
is a circuit.
and you want to find a circuit containing 3 and 1, and then that's 3, 1, 4.
So 3.
In case where this is not true.
Or what's not?
That's your exercise. Exercise
Oh, that's not true.
exercise show that this is not necessarily true.
Yeah, it's probably going to have to get bigger because bigger matrix.
And actually, you might need a non-graphical matrix. Sometimes these exchange axioms are true for graphs and not for general matrices. But exercise show this isn't necessarily true. Necessarily true. I don't think it's a problem. I think it's an exercise. I'll give you some problems. Problem? Okay, a problem is to prove this. An exercise is to do this. Okay, so okay, so this is great. So this is an equivalence relation. This is an equivalence relation. And we are going to call the equivalence classes connected components. We call the connected components of M. And so my claim, and I'll leave the details to you, but I think this should be pretty clear. What I did is I took my matroid and I separated it into groups, where inside each group you have, I mean, here's the matroid, right? And I separated it into groups where each group is an equivalence class, meaning that any two elements inside each one of the groups is contained in a circuit. So that means I cannot break these guys up. But these guys are in different equivalence classes, meaning that there are no mixed circuits, meaning that I can separate that into a direct sum. And so my claim is that actually M is equal to, well, maybe I should call these guys E1 up to E sub M. So what I get is that M is the direct sum of the matroids on each one of these guys. And the matroid on each guy is just a restriction to that set. So really what I'm saying is, if this is your matroid, you're just going to split it up like this, the way that it looks like you should. And this is the unique decomposition into irreducibles. This is the unique decomposition as a direct sum of indecomposables. And again, this is not hard to show. We already did all the work. And what should we call an indecomposable? Well, if we call each one of the pieces a connected component, and we said the way you take a matrix, you separate it to connected components, then what should you call an indecomposable one? Well, we're going to call it a connected matroid. So definition, a matroid is connected if it is indecomposable as a direct sum of smaller guys, or equivalently, by the definition of the equivalence relation, saying that there is only one connected component says that every two elements of the matroid are in a circuit together. Are together in some circuit. Any.
Like every uniform matroid, for example. Right? Is that true?
Is every uniform matroid connected? Almost.
Oh.
Except the ones of rank 1, for example, are not. But yeah, I think every uniform matroid, except for the rank 1 and core rank 1, I think are the ones that are connected. But maybe a more concrete example that you can look at is this one. Why is this guy connected? Because if you look at any two edges in this graph, they are together in some cycle. Okay. Now you should notice that this notion of connected does not match the notion of graph connectedness, because this is a graph that is connected as a graph, but disconnected as a matroid. Well, if you've done some graph theory, there is a notion of two connectedness, which means exactly graph connected. So, which means exactly matroid connected. So matroid connectedness is a generalization of graph to connectedness. But if you don't know what that is, well, basically, it's what I said right there. Okay? Now, let's see. So now we need to do a little bit more polytope theory. Let's say that you have two polytopes, P, which is the convex hull of P1 up to Pn, P, well, it doesn't matter, Pa. Let's say that this is a polytope in Rd, and Q, which is the convex hull of Q1 up to Qb, and this guy lives in Re. Okay. I'm going to take these guys and define. So this is in Rd. Definition. I'm going to define a product polytope. This is the polytope that is going to live in R to the d plus e. And basically what you're going to do is that in the first d coordinates you're going to put p, and in the last e coordinates you're going to put q. So the vertices of this guy are going to look like this. Well, each vertex has to be a vector in R to the d plus e. And so it should be some vector of length d plus e, which you can naturally split up into a d and an e. Okay? And the only natural thing to do is to basically stick a p sub I here and a q sub j here. For every value of I and every value of j. So if this guy has A vertices and this guy has B vertices, then this guy is going to have A times B vertices. Now, how do you might be a little bit intimidated by this definition, but actually you already are pretty familiar with this and you know how to draw it even because you know poset products, and this is the same thing. So for example, if you want the hypercube of dimension 4, then that is just a product of 4 segments. So you're used to thinking that as a poset construction, but it's the same thing with the polytope.
Yeah. You just think of it as a set of points in R, or whatever, isn't it? Essentially just the Cartesian product. Two sets of numbers.
Yeah, it is.
I mean, vectors and points.
It is. So, I mean, for example, here's a polytope. Let's just do one example. Let's do the 0, 1, 0, 0, 0, 1, and another polytope, which is maybe just a segment. And let's call these coordinates maybe 0, 1, and 1, 0. So this guy lives in R3, and this guy lives in R2. Okay. So for the product, you're going to do exactly what you did to multiply two posets. You're going to draw P and from each vertex of P, you're going to hang a version of Q. So here's one Q, here's another Q, and here's a third Q. So what you get is this. So a triangle times a segment gives you a triangular prism. What are the coordinates? Well, basically, the first coordinates are just given by, well, these are not good coordinates. Huh? 0, 0, 1, 0, 1, 0, 1, 0, 0. Better. So this is the same. 0, 0, 1, 0, 1, 0, 1, 0, 0. Those are the first three coordinates. And then you stick the coordinates of this guy. 1, 0, 1, 0, 1, 0. And then for the bottom, you do the same thing. And then you append the lower coordinates. Okay? So that's the construction. Now, I chose these two P and Q on purpose because P is the matroid polytope of this graph. 1, 2, no. Matroid polytope of this graph. 1, 2, 3, right? What are the bases of this graph? Well, 1 is a basis, 2 is a basis, 3 is a basis. And so the indicator vectors of those are this one, and this one. Q is the matroid polytope of this guy. 4 is a basis and 5 is a basis. So these are the indicator vectors. Okay. And the product is equal to the matroid polytope of taking these guys and these guys separately. which is the direct sum of 1, 2, 3, and 4, 5. Okay. Why is this? Because remember, what is a basis of m plus n? Well, remember when we talked about direct sums, we said that if you want a basis of a direct sum, then you have to pick a basis here and a basis here. So this guy is a basis of m, and this guy is a basis of n. Okay. But if you want to talk about coordinates, then what you're doing is you're saying, well, m is the first 3 coordinates, n is the second 2 coordinates, and then when you pick a basis of m, you're just picking an indicator vector, like maybe 0, 0, 1. So that says you picked 1 as your basis of the first matroid, and then for the second, let's say you picked the basis 1, 0. So that means you picked 4, which gives you the vector 1, 0, and so the indicator vector of a basis of the direct sum is obtained by taking an indicator vector of a basis of m and then appending an indicator vector of a basis of n. And so, to summarize this discussion, what this says is that if m is n1 plus n2 plus dot 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 plus n sub c, then the matroid polytope of Pm is just a product of matroid polytopes of the different components. And what this tells you is that if you want to understand matroid polytopes, then basically it's enough to understand them for connected matroids. So this is a proposition. And again, I could prove it to you, but I think this is more enlightening, is just to stare at this example, and that shows you why this is true. Okay. Now, what does this mean about the dimension of the matroid polytope? Well, basically, we have to see what product does to dimension. Okay. This guy was 2-dimensional. This guy was 1-dimensional, and we got a 3-dimensional guy. And one of these pretty simple facts from polytope theory is that happens. That if you have basically the dimension adds up when you take a product. So the dimension of a direct product is just the summation of the dimension of the first guy plus the dimension of the second guy. This is true. Okay. And therefore, the dimension of a matroid polytope is equal to the dimension of Pn1 plus the dimension of Pnc. Okay. So now what? That means that we understand the dimension of a matroid polytope as soon as we understand the dimension of a connected matroid polytope. Now, again, our guess, if we had to guess wildly, is that this guy has dimension what? Well, we said we expect it to have 1 less than the number of elements. So 1 less than the number of elements of the ground set. The second one is going to have 1 less than the number of elements of N2, and so on. This one is going to have NC minus 1. We hope. or we think. We don't necessarily hope, but we might guess that this is what we get. And therefore, what we're going to get is, what is the summation of all the ni's? Well, we split up m into its separate pieces. And so when we sum the size of the pieces, we get the size of m, the number of elements of m. But then we get a bunch of ones subtracted. Minus c, which is the number of components. Okay. This is the number of connected components of m. And so this is what we might guess is true. And now we have two incompatible guesses. Over there we guessed e minus 1. Over here we guessed e minus number of connected components. And this is the true answer. This is a theorem. Okay. So this exactly explains the dimension drop. Okay. The reason some matroid polytopes have smaller dimension is because the matroids are not connected. And how lower dimensional are they? Well, exactly the number of components. So this gives a complete answer to what we wanted. And by the way, it kind of led us to a theory of connectedness in matroids, which is an important one. Okay, so let's prove this. So proof. Well, we're going to be done if we can show this fact, that the dimension is size minus 1 for connected guys. Enough to show that the dimension is e minus 1 if m is connected. So that's what we're gonna show. Okay, now I'm gonna do something kind of tricky here. What I want to do is this. Well, here I have my matroid polytope, and it lives in r to the e, and it looks like this, like something. Who knows what it looks like? But I'm going to show something, which is that if you look at all the possible edges in this polytope, you're going to get every vector of the form ei minus ej. So we know that every edge is of the form ei minus ej, but I'm going to prove the converse to you. That if the matrix is connected, then any vector ei minus ej occurs as an edge of this polytope. So that's the first thing I'm going to show. Every ei minus ej occurs as an edge of P sub n. Well, the way I'm going to do that is basically I have to show that every pair I and j occurs as a basis exchange between some basis and a neighbor basis, where I flipped I and j. And to do that, well, I know that I take I and j. And because my matrix is connected, I know that they are in the same circuit. So find a circuit C which contains I and j. I can do that because my matrix is connected. So now what I'm going to do is this. Look at C minus I. C is a circuit, and I got rid of I. So that means that now this guy is independent. And so I'm going to complete it to a basis. Okay. B is a basis containing C minus I. Okay. Okay. And so now what I want to do is this. Here's B. Let's draw a picture. So here's C. Then I got rid of I. And then B looks like this. Okay. Well, and J is in here somewhere, right? Because J is also in C. Well, remember that now I have a basis B. I have an element I not in the basis. And when I have a basis and an element not in it, that defines a unique circuit, which is called the fundamental circuit. So B is a basis containing it. I is not in B. So there is a unique circuit in B union I. Well, what is that circuit? We have it right here. That circuit is C. C. Okay. And a fact about this is that B minus when is B union E minus J a basis? Well, here's B. I add I, and now I want to delete an element. And remember we talked about this, that if you want to delete an element and get a basis, then what you have to do is choose an element that breaks the circuit. You have to choose an element in C. Okay? We said that this guy is a basis if and only if J is in that basic circuit. But it is. It is because that's what I assumed. It is, and therefore B is a basis, and B union I minus J is a basis. And there you have it. EI minus EJ. Okay. So that's nice. That shows that every EI minus EJ occurs as an edge of PM. And now I claim that I'm done. And the reason is that P sub M contains these vectors. E1 minus E2, E2 minus E3, E3 minus E4, dot, 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 until E minus E minus 1. These are all directions that you have available to you inside your polytope. And therefore, the dimension of the polytope is at least the dimension of span by these guys. So the dimension. So these guys are, when you take the span, what is the dimension of the span of these guys? Well, these guys are all independent, right? This is you can see it in any way possible. This is an upper triangular matrix, or there's just clearly no dependencies here. So this guy is E minus 1 dimensional. And P sub M contains all of these vectors inside there. So it has to be at least E minus 1 dimensional. Okay? And we know that it's not E dimensional because we have one equality. So it cannot be full dimensional. And here we showed that it's at least E minus 1 dimensional, so that means it has to be exactly E minus 1 dimensional. So that's it. That's this, and then that shows that the dimension is size of the ground set minus number of connected components.
Does that mean that all connected matroids on the same size ground set polytopes look the same?
So Jameson's question is, does this imply that all the connected matroids of a certain size and a certain rank are congruent? No, it doesn't mean that. It doesn't mean that, and I'll show you an example. So here's two. Here's one of them. And here's another one. So this is the matroid of this graph. This is the matroid of the uniform matroid 2, 4. These guys are different matroids. They're both connected. You can see that this one is connected, and this one we showed this is not graphical, so I can't give you a picture for this, but I can't give you a graph for this, but you can see easily that this is connected. So here I have two connected matroids on 4 elements of rank 2 with different polytopes. But you see what's equal about them is that every direction that occurs here already occurs here. The directions are exactly the same, which might surprise you because, for example, here is something that you see that is not here. But this guy has the same direction. So it's not that the edges are equal, it's just that the possible directions of the edges are equal. Which is neat.
And they're all the same length.
And they're all the same length, square root of 2. And that shows you even more how restrictive this is. Okay. All right, stop there. If you were going to say bad things, let me turn the microphone off.
Don't ever say bad things about it. If possible, whatever you do.
It feels like this guy should be connected to the polytope I'm playing around with.
So now you see why I feel like it's the same thing we're doing, you know?
I feel like it, but
it
I
isn't.
can't make the connection. I mean, because these are edges, and I'm dealing with.
Right.
Well, except that. No, there's a connection. I just can't find it. I don't know. You know.
Well, but so here's a definite connection.
Your edges are the directions, and that's what my vectors are, right? So my vectors are the convex hull of all the directions.
So a real honest connection is that if you look at a basis and you look at the cone,
I know you said 2 and 3, and I was like, what's 6?
then the cone is exactly a subpolytope of your polytope. Because it is a convex hull of the CI plane. And this is why I've been thinking about this because it would be very nice to have a nice triangulation of because this guy is not simple. So you want to triangulate it. And so somehow what you want is kind of a triangulation